So for titrating a weak acid with a strong base, or a weak base with a strong acid, the general idea is the same as a strong titration, but the calculations are a little more complicated. So say we have 50 milliliters of 0.1 molar acetic acid being titrated with 0.1 molar sodium hydroxide. So to find the initial pH, that's just a regular weak acid problem. We write the dissociation equilibrium, do the ice chart, solve for x, and then get the pH. So the first point we're going to look at is 10 milliliters of sodium hydroxide added. So right after the sodium hydroxide is dropped into the solution, the major species are Na plus and OH minus from the sodium hydroxide, water, and then acetic acid. Since it is a weak acid, it does not dissociate into its ions very much. So first is the stoichiometry problem. Remember that in a strong titration, the reaction was always just H plus and OH minus forming water. But here, the hydroxide ion, which is a very strong base, will take protons from the strongest acid present, which is acetic acid. So it will react to completion with acetic acid to produce water and the acetate ion. So our initial amounts are 5 millimoles of acetic acid from 50 milliliters times 0.1 molarity, and then 1 millimole of hydroxide. So hydroxide is the limiting reactant. So 1 millimole is consumed of acetic acid, and 1 millimole of acetate ion is produced. So after the reaction, all the hydroxide ion is gone, and then we have 4 millimoles acetic acid and 1 millimole of acetate ion. So now, after the stoichiometry problem, we look at the equilibrium to determine the pH. So the substance that will determine the pH is going to be the acetic acid. So one way to do this is, again, write out the equilibrium, do the ice chart, and get the pH. Or we can recognize that this is just a buffer, since we have acetic acid, a weak acid, and its conjugate base, acetate ion, in the same solution. So instead of doing the ice chart, we can just use the Henderson-Hasselbalch Equation for the pH of a buffer solution. So we have the negative log of the Ka of acetic acid plus the log of the concentration of the base, the acetate ion. Remember, you have to find the new concentrations after this reaction using the new volume, which is the initial volume, 50 milliliters, plus the amount of sodium hydroxide that we added. So the total volume is now 60 milliliters. So we plug in the concentrations of the acetate ion over the acetic acid, and then we get that the pH is 4.14. So next is 25 milliliters of sodium hydroxide added. So after the stoichiometry problem, we find that all the hydroxide is used up, and then we have the same amount of acetate ion and acetic acid, 2.5 millimoles. So this is called the halfway point, since it's exactly halfway to the equivalence point. The equivalence point being when we have 5 millimoles of hydroxide ion. So at the halfway point, as you can see, the concentrations of the weak acid and its conjugate base are equal. So this ratio is going to be 1. And from the Henderson-Hasselbalch equation, we see that the pH will be the pKa plus the log of 1. And since the log of 1 is 0, the pH always equals the pKa of the weak acid. at the halfway point. So the pH will just be the negative log of 1.8 times 10 to the negative fifth, which is the Ka for acetic acid. So now let's look at the equivalence point at 50 milliliters added. So all the acetic acid will react with the hydroxide, and none of it will be left. So 5 millimoles of these two guys were consumed, and 5 millimoles of the acetate ion were produced. So the concentration of the acetate ion after this reaction will be 5 millimoles over 100 milliliters, the total volume. And so now we do the equilibrium problem. Whereas in a strong-strong titration, at the equivalence point the pH was always 7, because the conjugate of a strong acid or strong base does not have any effect on the pH. But the conjugate of a weak acid or weak base does have an effect. So this acetate ion acts as a base. And the base equation for it will be this equilibrium. So we do the ice chart, starting with 0.05 molar of acetate ion. And then we just plug this into the Kb expression for the acetate ion. And remember, we can find the Kb of the acetate ion by doing the Kw over the Ka of acetic acid. Since for any weak acid and its conjugate pair, the Kb times Ka equals Kw. So we find the Kb for acetate ion and use the equilibrium expression with the values in the ice chart that we just did. And ignoring this minus x with the 5% rule, we can solve for x, and then that's just going to be the concentration of hydroxide, and then we can find the pOH and the pH. So notice that the pH at the equivalence point is greater than 7, and that's because after all the acetic acid is consumed, we're left with the conjugate base, which makes a basic solution. So now let's look at one point after the equivalence point. So at 16 milliliters added, we have 6 millimoles of hydroxide ion, and in the reaction, the acetic acid will be the limiting reactant. So we have 1 millimole of hydroxide ion remaining, and in addition to 5 millimoles of acetate ion. So the hydroxide ion will dominate the pH because it's a much stronger base than the acetate ion. So we don't even need to worry about this. We just find the concentration of the hydroxide ion and then calculate the pH from that. So the pH curve of a weak acid strong base titration looks something like this. At the very start, the pH will increase more rapidly than in a strong titration, but then it starts to level off because it forms that buffer, and we know that buffers are resistant to changes in the pH. And the greatest buffering effects occur at the halfway point, since we know the greatest buffering is when the concentrations of the weak acid and its conjugate base are equal, which is what happens at that halfway point. So then up to the equivalence point, which is always greater than 7 due to the conjugate base of the weak acid that remains in the solution, the slope here is not as steep as in a strong curve. And so remember that at the halfway point, the pH is equal to the pKa of the weak acid. And for a weak base being titrated with a strong acid, the method for solving the problems is basically the same. And the pH curve looks something like this. The halfway point is still the same. The pH will equal the pKa of the conjugate acid of the weak base, and the equivalence point will be less than 7, because when all the weak base is reacted with the H+, the conjugate acid of the weak base will remain in solution to produce an acidic solution.